In a previous video, we introduced you to systems of equations. A system of equations is a series of equations joined by the word AND, or more commonly, a brace. In that previous video, we showed how difficult it might be to find points that would satisfy all the equations in a system by simply guessing and checking. This video will introduce a method called graphing for solving systems of equations. So let's consider this system of equations, and we want to solve that system by graphing. To solve the system by graphing, we simply need to graph each equation individually, but they have to be graphed on the same set of graph paper. So let's do that. And just so that we can see very clearly what we're working with here, I'm going to graph this equation in red, the first equation, and I'm going to graph the second equation in green. So all I'm going to do is graph this equation, y equals 2x minus 3, using the method of graphing equations of lines that we learned long ago. So I'm going to start with the y-intercept, which is -3. So I'm going to go down on the y-axis 3 units, and there is my point. And then I'm going to use the slope to find a couple more points. The slope is 2, so that's a rise over a run, 2 over 1. Up 2 over 1, here's a point. Up 2 over 1, here's a point. And you can do this as many times as you need, and then you'll want to connect these points with a straight edge. When you're solving a system by graphing, you want to be as accurate as possible when it comes to actually getting these lines very close to where they need to be. So you should use a straight edge because that's going to determine exactly where you find your solution. If you just kind of freehand it, you're not as likely to get as accurate of solutions. So that looks about right there. Now we're ready to graph the next one. Suppose I should put this in red here. Now we have to graph the next line. The y-intercept of the second line is 7, so this means I'm going to go up 7. And then the slope is -3, so I'm going to go down 3 over 1. There's a point here. Down 3 over 1. There's a point here. Down 3 over 1. There's a point here. And then I connect them with a straight line. Again, you'll want to use a straight edge here. And now, what we wanted to do was find points that satisfy both of these equations. In the previous video, I kind of guessed a point on one of the equations. So now what we're doing graphically is I might have guessed this point right here on the first equation. I plug it in, it works out for the first equation, but it will not satisfy the second equation. How can I tell? Because it's not on the second line. In order for a point to satisfy both of these equations, it has to lie on both of the lines. So we're looking for the point that is on both of the lines, and here it is. This point lies on both lines, so all we need to do is find the coordinates of that point. That's over 2 and up 1. So this point is at 2, 1, and that's on both of the lines. So we've solved this system of equations by graphing. It turns out that there's only going to be one solution here. Some systems could have more than one solution, and we can write the solution in one of 3 ways. We can simply list the solution. We can put the solution in a solution set, and this will be useful when there's multiple solutions. Or finally, we could actually list them in another system that's a little more simplified. We can say that x equals, and the x-coordinate is 2, and the y-coordinate is 1. Whenever you have an x-coordinate of 2 and a y-coordinate of 1, it will satisfy both of these equations. And just to explore that, I'm going to go ahead and plug into this first equation here, which is y equals 2x minus 3. What we're saying is that this solution, when x equals 2 and y equals 1, will satisfy this equation. So I'm going to go ahead and plug in 2 for x and 1 for y. So y equals 1, x equals 2, and then simplify the right-hand expression. And I should get an equation that is true. 1 equals 1 is true. So it satisfies the first equation. I'll leave it to you to check the second equation. Go ahead and plug in 2, 1 into this equation and ensure that you do indeed get a true equation. Now there's one disadvantage to graphing, one major disadvantage to graphing, and that is that it depends on your accuracy for graphing. Remember I mentioned that it's very important to use a straight edge, because what you're doing is you're just simply looking at the graph to try to figure out where that point of intersection is. In this system of equations, we lucked out. It was right on a grid line, so we were able to tell pretty surely that that point is exactly 2, 1. Other systems might not have solutions that are integer values, and at that point you'll have to kind of guess where the solution is. So for instance, if you were to have a system of equations, and I'm not actually going to work out an entire problem, but let's say you had lines that looked like this. Intersecting at this point. Clearly at this point we're not on a grid line, which means that our solution will not be integer values. So when we actually list our solution, we're going to have to estimate. It appears that we're going to go over 1, 2, 3, 4, a little bit more than 4 on the x-axis. Maybe about not quite a half, so you might say 4 1/4 or 4 1/3. I'm just going to go ahead and say 4 3/10 here for the x. And for the y, we're going up 1, 2, 3, 4, and this time we're going up, it looks like just a little bit more than a half. So I'm going to say 4 6/10. Now, these are not exact values. We're estimating the x value of 4 3/10 and the y value of 4 6/10. We haven't found exact values for those, and that is one disadvantage of graphing. Algebraic methods that we will learn do not have this disadvantage. They have the ability to solve systems of equations exactly.